What's up, everybody? Welcome back to the channel. Today we're going to be continuing our morning session, right? So we're going to hopefully finish up the Hinge design that we've been working on for a little bit now. Finish up those parts since we have all the skeleton sketching and everything done. And then we've got at least 2 user questions so far, one from Pennsylvania. One is how to do a herringbone gear, right? So we're going to try and maybe look at a way to do a parametric version of that. And then second question has been to talk a little bit more about equations and variables and properties and stuff like that inside of Solidworks. So we'll probably get to some examples like that. Maybe we'll combine the two a little bit and see what we can get up to. So the first part of the session is going to be finishing out our Hinge design that we've been working on. We'll jump over to the model. If you guys have any questions or anything that you guys want to focus on today, by all means, raise your hand, put it in the chat, and we'll try and get around to it. We'll probably do this for, I don't know, maybe an hour to an hour and a half-ish, and see what we get up to, and we'll go from there. Thanks for hanging out. Like I said, feel free to send your questions in the chat. Somebody was going to send over some files to look at and open up, so by all means, we can take a look at it, and we'll go from there. Stefanos, if you want to put specifically what you're looking to cover in the variables, that'd be awesome. All right, cool. So this is where we're at on our Hinge design, right? So we've created this kind of, I don't know, almost, I want to start calling this like a folder part because basically it's only here to hold all of our sketches, right? We've got 3 sketches that we've made up. So our primary one is this profile view where this morning we went through and we figured out our linkage lengths, and then also we're designing it so that the links kind of bottom out on each other and control the movement. So we did that this morning. We put in this secondary view here showing the profile of our bent sheet metal brackets, we're calling them. And then our top view has very little information. All it has is our hole locations here for the through holes. Just making sure everything sounds good and everybody can hear me. All right, cool. So the next step, we've kind of done this part here. We'll probably go in and add a fillet, or this will need to get filleted at some point. So we might as well do it now. And we want to make sure our fillet is about roughly the material thickness. Our minimum here. Now we could have done this as a surface and then thickened it, but we'll just do a double fillet here. So it'll be 5 millimeters here, and then on the back side it'll be 10. Goes 5 and 5. 10 millimeters. Millimeters. Come on, there we go. Cool. We can look at this here and make sure it doesn't mess up coming around this corner. It looks like it's all right. If we didn't like the way that looked, then we could just drag our cut profiles down below the fillets, but it looks like it's all right. So we'll go ahead and call that pretty good on this part, unless we notice that we're missing something later. We could probably fillet these edges too, but again, this is really just a stand-in part that we're partially using as a demo for a larger project. So it's not critical, but we can still make it look nice. All right, so that's one part done. So now we're gonna kind of duplicate the process and just design a different part or model in a separate part. Now, the one nice part about the skeleton sketch well, one thing to be aware of the skeleton sketch process is it's going to look like you're not doing a lot of work for a very long time. Because all of the work that you're doing is really dimensioning and getting the relationships right in these sketches. And then once you're done with that, you when you start actually creating geometry, it goes really, really fast. So we'll do a new part, front plane, and then really it's up to us which part we want to do next. So we're going to isolate this top part so we make sure that we're not pulling in any of the sketches from the previous part that we created. And so now we just exit the initial sketch that it kicked you into, and we start adding in our sketches. Now, like we talked about in the morning session, if we look at this here, there's some decisions to be made of how we're orienting these derived sketches to the foundation planes. In this go around, we're just going to leave the planes where they are, which means that, for example, if we were to model this bracket, the front plane would actually be up here and not tied to any geometry in the back, which would be fine. It's not the end of the world. But it is something to be aware of, that your base planes don't necessarily or won't naturally align to geometry on the part that you're modeling. And so what you want to do, if you do want that, is to just reorient. Like, say we wanted to make this point here. Say we wanted to make this point here our origin, we would just simply create that relationship. All right, so we'll fix this in location. It's the same place that it came in at. And then we'll go get the other sketches here. This is our front. And since we're not moving them in relation to the origin, we could just leave them where they are. Best practice would be to put them in place. Let's see here. We want to make sure that we're creating the relationships to the right things. Let's see here, and now the top plane here. Actually, you know what? Yeah, we'll do that. We'll do the second bracket. We'll do the second bracket. As I say, I don't actually need those whole locations if we're doing any of the links. So previously we had, in the morning session, we had made sure that we put a point, because there's so little geometry in this sketch, we had made sure that we put a point on the origin when we created that original sketch so that we had a reference later on which we can align everything. And again, just aligning to our base planes. All right, so now that we have all of our skeleton sketches in place, now we can start creating some geometry. So standard practice of doing a skeleton sketch technique is to try and keep these derived sketches in the top of your tree, so that if you go back and make edits to the part in the future, or somebody else opens up your work, right, as long as you guys are using like a similar workflow and rules, we want to try and keep the derived sketches in the top of the tree, just because it's very easy to open up a part and say, okay, that's what's controlling this part, right? So you gotta, it's just a lot easier to, it's kind of like an indicator, right? All right, so the best way to keep these derived sketches on the top of the tree and in plain view, and keep them from getting nested inside of features as you create them, is going to be to create a sketch and then simply convert in, or the geometry. So we created a sketch, and then we're just grabbing what we need here. And now we'll go in and we'll extrude this. And we're going to use vertices to control the extrusion. So a start vertices and an end vertices. And you can see that these other parts are hidden, so the sketches that we're grabbing don't create external references outside of the part. All right, and then we can put those fillets in now that we did before. Order is not critical on these, but typing millimeters is. So in this, we're just going to create a sketch that has these 3 points in it, and we're going to use a sketch-driven pattern later to orient the holes where the bracket gets mounted. So these are going to be holes for a flathead screw. And what we learned in the morning session is that it's a non-standard hole. So instead of using the hole wizard, we're just going to create a plane here and then draw our own geometry to revolve. So we'll just align this with this hole, or with the point that we mapped out earlier. And now we just draw our geometry in here. So we know that it is a 1024 screw, but they're putting in a clearance hole for a 1/4 20. 6. All right, and according to my chart here, we should do it 82 degrees. And the head diameter on a number 10 is 385. So we'll put this in here like this, and then it's a revolved extrude. And now only draw things if you have to, and we don't have to draw that again. Now we'll just use that sketch-driven pattern. And what we want to select now is first the sketch that has just the points in it. Then the selected middle point is here, and the geometry we want to pattern is this. So now we get 3 of them that are tied to those points. All right, and now we need our side holes where our rivets are going to go through. And we know that our rivet size, or the hole for the rivet, is going to be equal to the diameter of this, which we looked up previously. And then that's an extrude. We're going to do through all, both. Use through all when possible, because it's pretty robust. Just make sure it's not cutting through something it's not supposed to. All right, let's see here. So we can exit this and we can save. And now we see we have 2 brackets. So next part is going to be creating the links. So this is going to get a bit repetitive here for a minute. Because we're going to be doing the same thing for the 2 links. So it's a right plane. And then insert our drive sketch. The good news is we only need to bring in 2 of our sketches because we don't need the whole patterns. And since we're not going to move the where the derived sketches come in at, we're not going to reorient to the ground planes. We're just going to leave them there so that everything comes in on the same origin. We don't necessarily have to fix these in place. Now that is something to be aware of though, right? We didn't fix this, so this is still underdefined. So in theory, this could move. So best practice probably would be to come in here and just add the dimensions, but to try and speed things a bit up for you guys. So now we're going to do a sketch. Just like this, convert, trim. Let's see here. I could probably put a fillet on here too. Do a sketch fillet here, I suppose, would be fine. Yeah, that'd be fine. Okay, there we go. Now all we need is our through holes for the rivets. There we go, and now an extrude. And we're going to use this one here. So that's our first link. And you can see now that since we've created the sketches once, and we're just bringing them into each part we're making, this part goes really quick. Like once you have the geometry already there, it goes pretty quick and you're able to piece things together pretty quick. All right, so new part, right? Front plane. Then we're going to isolate here. A nice trick is to just use the isolate command just on this folder part, or where that houses our main sketches, and that'll suppress everything else except for the part that's currently being edited. So you know you're pulling your derived sketches from the right place. So insert, derived sketch, same things. Front. All right, so now we can hide this. Go in here. And this is just going to be a straight slot that has the same diameter as this. That's our through hole diameter. Again, all of this is now linked, right? So if we were to go in and change the rivet that we need to use, right, and say it needs a different hole diameter in order to work, it's very easy. All we do is we go into our sketch here, we change our diameter here, and all of the parts will see the same update, which is really nice. All right, so as you can see, we made all the parts, but they're not necessarily in the right locations, right? Also, what? Also, I never confirmed the extrude on this part, so this has to get done. Vertex, same vertices as before, because those parts actually engage with each other. you can see that we have the four main pieces of our linkage, right? We don't have the rivets and we don't have the little shims that go in there, but the four parts that we're responsible for manufacturing are in there. So we can see that they're not aligned the way that we might want them to be, right? And that's fine, because what we're going to actually do is we're going to create another instance of this part within this file. And the reason we're going to do that is that the parts that we have right now are kind of constrained in place by the relationship of the derived sketch, right? So the derived sketch is frozen in place by this part 9. And because of that, we don't necessarily want to move these parts around. So one way, if you do want a movable part within an assembly, is you can either create another configuration, or you can just do it within this configuration, depending on how you want to manage it, or depending on how like strict you're trying to be to good process. And so what we can do is we can draw in. Now, I'm just holding control and dragging in from the tree. Ooh. So we're dragging in multiples now. So we're just pulling in. If you hold control when you drag from the tree, it'll bring in another instance of the part. So now you see that we have the original 4 here, which we can now hide. Actually, I'll probably just go through and suppress those. I got lots of extra parts here. All right, what do I do? So we don't need a second copy of this. And we don't need a second copy of this. And we don't need 10, 11, 12, 13. We got one too many of these. All right. Yeah, so now we have our 4 pieces, but you'll see that they're no longer constrained in place like these top 4 were. So what we can do now is we can go this, and we can come in here and we can start creating relationships. Now, since we know that they all share the same origin, what we can do is we can take, and the movement is all about this right plane, we can take our right plane and fix that in place, right? So maybe let's just do one part at a time. So we're going to do these 2. So we're going to keep our part 9 open that has our skeleton sketches in it. And we're just going to focus on this secondary mobile part 10. So what we did is we know that they're all going to share the right plane, and that's where the motion is. So we can just constrain it to the right plane. You always want to, when possible, you want to create your relationships or your mates or any other like shared geometry relationship to the thing that is farthest up in your tree, right? And so in a part file, that's going to be your, or even an assembly file, that's usually going to be your 3 base planes and your origin, right? So when possible, create mates and relationships to those features, because they're not going to move and they're not going to get deleted. They're not going to go anywhere. So they'll be very stable, and they solve very quickly because they're at the top of the tree. And Solidworks doesn't have to solve your whole part and then create a relationship to a face or something like that. You can just solve based on the 0 coordinate of the entire part. All right, so we've aligned the right plane. Now what we want to do is we want to make sure that the pivot point are basically these. Actually, you know what? We don't need these at all, because this one we're just going to treat as ground. So I'm going to delete this actually, and we can turn back on this part 10. So we can leave this on. We'll hide it for now, and we'll do this bracket. Let's see here. Actually, we'll do the arm first. Yeah, we'll do the arm. We'll do both arms because the bracket has to attach to the end of the arm, so that those need to be fixed first. All right, so same thing still applies. Right plane to right plane. We're going to make those coincident. And we can see that because when we imported when we did the derived sketch, because we just left it where it was in relation to the origin, and that origin is the same across all the parts and is the same as this assembly origin. When we align the planes, everything just snaps to where we want it to go. All right, so now we're going to turn on this here. And we want our, let's see here, we'll take this geometry here. And we want to align it to the pivot point, which is up here. So we can do this and concentric. So now we have our arm that's moving about the right location. So next up, we'll just do it to the other arm, or the other link. Again, right plane to right plane, and we're using the assembly plane, right? We're not using the part 9 plane. We're not using this folder parts plane. We're using the thing that's highest up in the tree in the right location, which is the assembly and its right plane. So now we're doing the same thing. We're picking here, going here, concentric. So now we have 2 mobile links. And since we have our links, we can now go in and put our other bracket in the right spot. We'll show these and we'll hide this here. Okay, so we want our bracket. We know that the right plane can go to the right plane of the assembly, right? And we can see that the proper spacing is maintained for that, for the washers that we modeled in, or that we sketched in, but never modeled. So later on, it'd be really easy to go get all the COTS components like the washers and the rivets and just put those in here. But for right now, we'll just keep focus on the manufactured components. All right, so now we have to create relationships between the bracket and our 2 links. And one of the best ways to do that is going to be to use the derived sketches within each of those. So if we just focus on these 2 parts, right? So if we drag this over, I just want this and this, I believe, right? Yeah. So we'll isolate these 2. And since they have the same sketch in there, or so they have the same sketch, but we're going to use the geometry that's associated with the points in order to link them. So we want this point here would coincide with this point here. So we'll do a coincident. All right, there we go. And now we need that little link. And we'll turn on his sketch. And so we want this link here, or this point here, to be coincident with this point here. Notice how we're not using the geometry this time to put things where they need to go. We're using the sketch entities themselves to create the mates. We're not mating to the surfaces or to the cylinders. We're using just the sketches. All right, so what we got here? All right, so we should have a mobile parametric assembly that pushes information between all the parts and shares relationships, but is also can be easily manipulated and has the proper BOM. It's everything you ever wanted from Solidworks. There you go. So we'll save this before we try and move it. But now if we try and bring this down, there we go. So we know that because of the way we designed this, that when this meets tangency here, if we were to put a, well, I guess we can here, just to show the point. If we were to mate, come on. If we were to mate this face with this face and make them tangent, right? Then these two faces here should be perfectly parallel to each other, which they are. So two selected items are parallel. So also, which is cool, is if we do, say we remove this mate, right? And we bring it up to the other position, we know that when this is tangent to this, or actually concentric because we put that fillet in here. Ooh, doesn't like it. Tangent. Ooh. When that's tangent to that, this should be the angle that we specified in this SketchUp here, which is, what was it? It was like 78.5 or something like that we came up with this morning. Should be something like that. Yeah, 78 degrees. There you go. So that's 78 degrees. So we created a 4-bar linkage that locks out against itself on our two extremes. And we can control the location by turning these tangencies on and off. I found a local tangency. Okay. So now one thing that we could do is, since we know that when this is tangent, we can put a mate on here that will control the angle of the faces to each other. So we can manually go in and prescribe the allowable angle of movement, so that as you, like, you can see that there was a local tangency that solved that second mate as I turned it on and off, right? And so if we wanted to get rid of that and just have the parts be able to move freely, we can go in here and put a mechanical, I believe it is. Nope. Advanced. Let's see here. Which one is it? This one? But it's degrees. Yeah, here we go. So the two faces, it's always trying to figure out what angle is which way, right? So that's 30 degrees. So as we bring this down, so the minimum we would want would be 0 degrees. And the maximum we would want is 78, I believe. It's always tricky to get these planes and figure out like the normals and whatnot to figure out what the values should be. But if we do that, yeah, so that's what it is. It's a limit mate. So the limit is the type of mate, and then this is an angle limit, and then you can also do a distance limit as well. So say you have like, I don't know, like a piston extending or retracting, right? You could control the linear motion as well as the angular motion. But if we did this right, it should let us move, and then it'll stop. Yep, see how it stops at the tangency? And then as we go the other way, it will do the same thing. Or it'll just keep snapping back. Okay, so it needs to come through 78 degrees. So we'd have to pick something that, so I have to pick different faces, I think. That is one tricky part about, or I've always had found it tricky is that if there's like a local pass-through point, then it might not work. Or I have to pick different faces to control it. So maybe this is the face that we want to control. Was it 78? No, I can't remember. All right, we're going to suppress this. Unsuppress this tangency. Yeah, so it's 78, but it's out the other side. So it'd be, what, 78 minus 180? So 102. So I believe if we make this 102, it should work. Let's try that. Yeah, there we go. All right, so it was 102. So it was 78, but the other side of the angle. So now we have a mechanical mate that will control it from 0 to the 102 degrees open position, which is awesome. And the cool part is, just as a demonstration, so we'll save this again so we don't crash. If we wanted to change something, we could just come in here, say we wanted to change the through hole for the spacers, or for the I'm making it all 1/4 inches for the rivets. You can see that it's already changed, right? So now they're all 1/4 inch holes. And that changed 4 parts instantly by changing 1 dimension in 1 place. Whatever it was, 125 or something, 166 maybe? I can't remember. It's not critically important because we're not manufacturing this. We're just using it as a stand-in in an assembly. So, all right, cool. So there we go. You can see we just changed back from the 1/4 inch pretty quick. All right, so now we have a fully flexible parametric assembly. One thing that's fun to do or cool to do is, say we have another sub-assembly, right, that we want to add this into, because usually hinges are attached to doors, they're attached to, you know, other things, right? So if we import this assembly into, we'll just save this really quick. Let's see here. All right, so we have this assembly, right? And we know that this hinge can move because we were just moving it, right? But when it's imported into another assembly, now it is a subassembly. And by default, subassemblies are fixed into place, right? So what we can do here is, first we're going to float it. And then we're going to fix these planes in place. So let's just do this. And this is just as an example, when you import it, or when you go to insert this assembly into, you know, wherever the, or when you go to, when you go to insert the hinge assembly into the larger assembly where you'd have like the door and the base and whatever, you'd obviously attach it and create mates within the larger assembly that would locate this. But just for right now, we'll just do this. And we'll do a front plane is here. Okay, so now we just mated in place this bracket, right, which is freezing the rest of this subassembly. But we can go here and make it flexible. So make subassembly flexible is what we want. And when we do that, now it will enable our subassembly to move inside of this larger assembly. And the movement is still constrained by all the mates that we set up when we built the subassembly, when we built the hinge assembly. So now we have a fully parametric hinge that can move even in larger assemblies. That's very easy to update. The bomb's going to come out correctly. Yeah, I mean, this is the ideal behavior of what you would want in this type of project. You can change the relation. We can go in and easily change the relationships of how this bottoms out and the behavior of how these links interact, right? To get maybe different open or close angles or heights or what have you in terms of like the 4-bar linkage that's in here. And so, yeah, this is pretty much it. This pretty much completes this project. This is all we really needed from it. Something to be a good stand-in and help locate the screw locations, the hole locations. So I think that pretty much wraps this up. So now we'll kind of open up the floor to what you guys want to do. We can go back and start looking at some of your guys' questions. If you guys have new questions based on this, yeah, let's start there. If you guys have specific questions based on this, type them in the chat now and we'll kind of close this out. And then I think we're going to look at herringbone gears first, and then we'll pivot and we'll go into variables. That seems like the two topics that you guys most wanted to cover today. So any questions on this before we get out of here and move on to something else? Top down, skeleton sketching. We kind of did a little bit relationship building stuff in here. All right, cool. All right, we're going to transfer over and we're going to go back to our hinge model. So give me 1 minute to open that up. Or we're going to go, yeah, we'll go back to our gear model. Sorry, not hinge. I said. All right, here we go. Cool. So this is the gear model that we looked at yesterday. This is a parametric gear that I built when we were, for a project where we were going to 3D print helical gears or spur gears to make a drivetrain or a gear train. And we needed very accurate geometry in order to print the gears. And McMaster Carr is notorious for having their gears be kind of close, but not exactly. And so this was a spur gear profile that we drew up. This is the profile. And as we looked at in yesterday's live session, the big kicker here is this equation, or these equations, which basically define the shape of this curve. So this is an equation-driven curve within a sketch. Excuse me. This is an equation-driven curve inside of the sketch, and these are the governing equations. This basically are, I mean, these are equations that are available on the, like, off the internet. If you just look up the gear profiles. So this is the profile, the equations that govern the profile of the teeth. And so we wanted to make sure that this was correct on what we were making. And then we can walk through the tree really quick. Basically, what we do is we extrude that profile, that shape that we made. We have a base fillet. We mirror that cut across, and then we pattern it depending on the number of teeth that we have. And then in order to do a helical, which is kind of half of what, who was it that brought that up that they wanted to look at herringbone gears today? Icy coral. All right. So Icy Coral wanted to look at herringbone gears, which is basically where you have two spur gears that meet in the middle. And the advantage of that is if we look at, so we're getting this profile and then we're sweeping it and then we're deleting the part that was hidden. So this is this would be a helical gear, right? And so the advantage of a helical gear is that you're spreading the wear of the tooth out across the length of it, as opposed to maybe in a spur gear where you have like one part of the tooth that's fitting more forward or back, and therefore you're having wear, right? And you're also engaging more than one tooth at the same time in a helical gear. So as they kind of come in and mesh together, you're getting different points of contact along different teeth as they're going. So you have better power transmission. Now, what AC Coral was trying to do is he's trying to make a what's it called? Not a wishbone gear. Herringbone, thank you. Herringbone gear, which is basically where you have two of these that meet together, and they're very hard to machine because you can't have them out on a normal machine, but they're very easy. In my opinion, I think the easiest way to do this is just going to be to mirror the part across. So if you just go here and do mirror, face, bodies to mirror, body. This is a herringbone gear, right? Now you can go in and you can adjust whether or not you want like maybe you want to remove a little bit of material here in the front so that you know you don't have contact occurring here in your teeth. But that to me would be the way to do it. And the benefit of using this type of gear is that you don't have any axial force anymore. So a spur gear doesn't have axial force because the teeth are straight, but as you crank up the helix angle, you're getting additional power transmission because you're spreading the load out over more teeth, but now you're also inducing axial load down the shaft that the gear is riding on, as the angle of that tooth is now pushing axially. So with this type of gear, you have counteracting axial forces, so you have all the benefits of a helical gear, but without the axial force that you have to take into account. So this, I think Coral said that this was going to be 3D printed. So this would be ideal because it'd be relatively inexpensive to make this type of gear using additive. So that makes a lot of sense. But yeah, I think that's the way to do it, Coral, is to, and I know we looked at the equations. We looked at these yesterday. So these are all of the variables that govern this gear. So these first 5 are actually user entered, and then everything after that is just an equation based on these first 5. So if we wanted to do like a 30-degree helix instead of a 35, usually you have really high angles, right? When you get into a wishbone gear, but you can see that it changes, right? So basically that's a variable that we're changing inside of the equations that governs the geometry that's created. Now this is going to be twice as thick because we mirrored it across. So this is 1 inch as opposed to the input, which is 1/2 inch, but that would be the way to do it, I think, is you just do a, okay, cool. You just do a standard gear and then mirror it across. Now, one thing that I've seen on herringbone gears is that there's a groove going down the middle. And I don't know if that is to try to keep the geometry here, this leading edge, from being the only point that's loading along the gear profile, or if it is just to provide clearance for tooling when they're actually cutting these gears, or a combination of the two. So if you're having issues and you look at if you're going to do these additively and you print them, you can look at the wear on your teeth over time from a set and see if you're having issues there. And then an option might be to just put a groove in there to kind of take that leading edge away, or you can just go in and fillet it. I'm not sure how well this will fillet, but yeah, it doesn't like that. It might be too big though. Yeah, so you could add a small fillet in there, and that's going to remove material on this side so that you're not having it being the bearing point on this side, right? Like it's setting all of this back a little bit. I wouldn't do it on this side necessarily, because this is going to be a fillet on this side would add material. But yeah, that might be one solution if they're just going to be additively manufactured. All right, so Icy Coral is sending over a file we're going to take a look at. Stefanos, what exactly do you want to do with variables? Do you have an example project or something that you want to throw our way? It doesn't have to be anything complex, just a use case that you'd want to look at. So Icy Coral said that he's sending a file. So give me a minute to look at that. Wait for that to come in. So what do you guys do? What are you guys using SolidWorks for? I mean, if you're watching this type of in-depth content, I'm assuming you're doing something complex. Or are you just starting out and trying to pick up good practices? What's your guys' use cases? All right, so I got your file, Coral. I'm going to open it up now. And then I'll throw it up on the screen and we can look it over. So Stefanos, that's really interesting. It's interesting that because I've always thought of like if you have, you know, obsolete parts or you're not able to source something, if you have some mechanical aptitude to be able to design and then create replacement parts, that has to be pretty handy. All right, cool. So this is the model that we're going to throw up here. Let me make sure. Icy Coral, this is okay for me to put on here, correct? It says it's a student edition, so I want to make sure that it's not like work related. All right, cool. All right, let me throw it up here. All right, cool. So this is the model submitted by Icy Coral. So this thing that we're specifically looking at is going to be this master modeling technique, right? So let's take a look. So the little hats here, this is just education version. It was saved out of. So that's what the little hats mean. So let's just take a look at it really quick and see what it is. Oh, whoa, all right, cool. Man, they even got the poles in there and everything. Okay, cool. All right, sweet. This part here is just, okay. Gotcha. Okay, cool. So this is being 3D printed, I'm assuming? Or injection molding, one of the two, without draft though. No draft? Yeah, no draft. Sweet. Okay, cool. Very cool. So let's look and see how he built this. This says master model in it. So did he design this all in one part file and then save it out? Is that what he's doing? Okay, so if we close this, 4:1 master model. So this is just the individual part, right? This is just the housing cover. Yeah, okay. Why do we keep this? All right. So this is where everything was designed, I believe. Okay, so he's got folders. So this would be equivalent to like our master sketches 2, inner ring, ring revolve. So how does he export? Is he saving out the bodies independently? Pattern the inner ring. Inner shaft key. All right, hold on. I'm gonna read through your saving now, make changes in dual part files. Okay, so it sounds like this was created as one part file, as opposed to doing stuff inside of the inside of assemblies. And then it also sounds like you're saving out the individual part files from this one master model, like this one master part file. Let me read really quick how you did this in your email, and then I'll comment on it again. I thought it was a gearbox. Okay. I was I've seen something like this done on a video. Very cool work, dude. Very cool. Yeah, okay. So it sounds viable, right? Like it sounds so. All right, so let's back it up. The approach you're doing obviously works, right? Like you created this super complex mechanism, and I don't know if you've been able to print this and have it work or not, but like from the start, it looks awesome. Like everything goes together, everything has relationships to itself, or everything like properly aligns. Like you're good to go there. All right, let me read your comments real quick. All right, so the method for saving out the bodies is you start a new part, you insert the master model and delete keep the bodies, and then save one body. Name file is that part name or body. Most of the main part is driven by the master sketch. I used convert entities so many times in that model. Nice, solid. Yeah, there's nothing wrong with convert entities necessarily. Like it works pretty well. The real question is, what are you converting? Are you converting like this edge, or are you converting from the sketch? Because the sketch is going to be more stable than the way that SolidWorks names this edge, right? Or this face, or anything else in that for that matter. Like the sketch geometry is most stable. Again, the only thing more stable than that would be like your base planes. So convert entities isn't bad. It just depends on what you're converting, if you're doing it the right way or the best way, I guess. Okay, so if we go back to this master model or this main assembly, so this is all of the individual pieces brought in, and then it has the master model as the top level, right? So you're making you're making modifications in the individual part files. Now, is there a relationship built back to the original then? Let's see here. So you bring everything, I see. So you bring everything in and then you delete, keep it back out, right? I see. Interesting. So then the real question is, comparing this to, say, the skeleton sketch method, right, is one, which one's faster? Two, which one's more lightweight? And three, which one's more robust? Would be the only reason that you would switch your method. Like, obviously this works. You built a complex machine in SolidWorks. That's more than a lot of people ever do. So really then it just becomes a comparison of which method is maybe better, I guess would be the term. So you insert this, but it remains. Yeah, so you're just inserting the part. Okay. Interesting. And then you just have to delete, keep this out, right? Keep the body that you want. Yeah, cool. And then you make your minor modifications to it that don't drastically affect anything. And then you save out that part. Okay, cool. I like it. Yeah, I mean, it seems viable. And so if we make a change, then in theory it should propagate through everything, right? And so if you go to make a change, you would do it in here, right? And you would do it from the sketch. Of course, ooh, look at you, labels and everything. Nice work. Very nice. Okay, cool. So then the question becomes, what can I change here that won't blow everything up? So if you keep all the sketches from the master part, are you able to edit those sketches from within the part and drive that like backwards through the loop? Like if we opened up, I'm trying to find something that won't break everything. This main bearing diameter, maybe. Bearing diameter with clearance. All right, so maybe if we just slice it, we can look at it. All right. Okay, so this is okay, so you don't have the bearings shown in here, correct? They would go in these pockets. Okay. But if you make a change within the interesting. So if you make a change within this master model file, then it'll still update though. Right. Okay. And this is the master model file, so you can't see the bearings. That makes sense. That makes sense. All right. So something that shouldn't blow it up would be something like this. 22.1. 18. Sweet. There you go. Yeah, I mean, seems to work, man. Nice job. Oh, that's cool. I'd be interested to see, I would be interested to see which one works better. I'm trying to think if there's anything inherent. Like from a structural difference. Unless we just crash Solidworks. Oh, no, there we go. Okay. This should be back to 22.1. I guess I never checked that it changed, but let's see here. Yeah, 22.1 millimeters, right? So if we go in here to the main sketch and change this to 15 millimeters. Yeah, that seems to update really quickly. So seems like it makes sense. I guess. Wait, unless it's not updated. Ah, I have to rebuild. That's why. The moment of truth. Maybe I made it too small. Let's make it 20. So now if I rebuild, I'm interested to see if the parts like how the parts update. Okay, so the parts haven't updated yet, I don't think. Because if these bearings are just brought in, unless you modeled the bearings to the sketch, in which case then it's possible. But I think these bearings in general should be too small. Hello, Abood. Yeah, there we go. Yeah, so the bearings themselves are probably imported from McMaster or something. Yeah, there you go. Good job. Yeah, that's the best way to do it. Like, just grab your geometry online. Don't model it yourself. This is perfect. Yeah, and it seems like everything updates, right? Like, we made this outer bearing journal smaller, or the OD for the bearing smaller, and everything updated. So I don't see an issue with it necessarily. Like, obviously it works and it looks really good and everything is here. So yeah, I mean, as far as like where you're converting entities from or the relationships on like how you built things, I mean, I think you're probably fine. I'm trying to think structurally whether or not there's a difference between, or there's an advantage between like skeleton sketching and doing it all within one part body. I guess my thought would be like on the linkage that we just did, on that 4-bar linkage, right? I'm trying to think. I mean, I guess we're doing most of the design there within the sketch, not necessarily within the assembly environment. So there's that. And then if you wanted to make it mobile in an assembly or have a mobile version of the assembly, you would just have these as the is this mobile or this is fixed? Yeah, okay. Yeah, you would just be using your standard mates. Yeah. I wonder if it's faster, or I wonder if it's more lightweight to instead of having Solidworks take this assembly and inserting that assembly multiple times or in each part and then deleting the bodies as a feature. I wonder if that's faster or slower than generating just the geometry that you need in each part. But I can see an advantage of doing the master modeling way where everything is in one location as opposed to having the sketches be technically in a separate document. I know. Okay, so here's one advantage of doing a skeleton sketch, where the only thing in your part file are your sketches. So say I wanted to work with a team of engineers, right? And there's probably a way around it in this instance, I guess. But say I wanted to work on an assembly with a team of engineers, I can take that skeleton sketch part file and save it out, or basically like instead of keeping it within the let's see here. No, here, I'll have to open it back up. Hold on one second. Yeah, McMaster is the bomb. I think their parts are almost always more expensive than other places, but simply because so many engineers use their CAD and then that CAD part number ends up in the BOM. It's just like, oh yeah, but order it from there. It is the most fastest, yes. Yeah, the advantage of have like the multiple people working on it, you give them the handle file and they can make edits to it, or they can edit their part off of it, but can't change the original. It's the same with the derived sketch, right? Yeah. Like it's the same as the derived sketch where you can't edit a derived sketch. You have to go back up to the parent file and then edit the sketch within there. Mm-hmm. I'm trying to think. So I know I've worked on larger projects before where we save out the skeleton sketch, that like folder part, right? We save that out as a part to the vault, and then you can open that part, insert it into an assembly, and then model from there, right? And that folder part basically has all the information that you need to pick up your relationships to any exterior parts. So that's one like workflow that we've used in the past that's successful, because we have revision control on the folder part that has all the sketches, and then you're modeling your geometry to those sketches, and then if that changes, we have revision control on that, and it'll also update your part file with the changes based on like that folder part. Now the question is whether or not you would have the similar functionality with this master model technique. I suppose you would. You'd just be inserting a part into the part file instead of deriving in the sketches. And I think that's really the only difference, right? Like you have very similar functionality where you're creating something, you're inserting it into a part file. You're not able to edit it within that file. You have to go back to the parent, which is good, because that allows more than one person to use that file as a reference at the same time, and share that information, so you can just like distribute the workload. You're able to create references to it, which is good, or references like within it, which is good. Hmm. I think the only reason I would prefer skeleton sketch is because the thing that you're sharing is more lightweight. And I don't know if that's a good thing or a bad thing. It probably depends on what the design is and what the context of the project is. But like to me, you're doing a lot of your design work in a single part file, which is the thing that everybody has to access. In order to make their say each engineer has a different part in your subassembly. The only downside I can see is that if I want to change my core geometry, I have to go back to that file. And I guess that's the same in the skeleton sketch situation, but you're not changing geometry in the skeleton sketch. You usually only try and put like some relations in there. So I guess it's the tricky slope of what do you and don't you include in that locked layer, right? In that folder layer, whether it's the master model or the that skeleton sketch folder part. Yes, you can protect your part when working with others by using derived technique. So the thing that you're like derived only works like it's the same as I mean it's very similar to your master model, right? The master model level, if you think of it as the same as that part, the folder level part where we're putting all our sketches that we eventually derive, you can't edit a derived sketch. So you have to go into that folder level in order to make any changes. And so that's what you can distribute amongst engineers and have them design independently. Like say you're doing,
I don't know, say you're doing this thing, you could have one engineer do one side of the case and one engineer do the other side of the case, and the only information you're sending each other is where the holes are and the outer diameters, right? Or like, I mean, maybe you want this outer profile to be controlled, so that when the two pieces come together and they meet up or whatever. So you're just sharing, and that's one of the key aspects of doing good skeleton sketches, is you're only putting information in that sketch that is in relation to the two parts or multiple parts that you're designing off of it, right? So that's one of the advantages of doing the skeleton sketch. But I think you get a very similar functionality with this master model. My only issue with the master model is that one, it's kind of a slippery slope of how much geometry do you put in your master model, whereas doing the skeleton sketch technique, you're only putting sketch geometry. There is no like actual geometry in there. You're only doing sketches. There's no 3D that's going to get distributed out. So that's kind of like one hard line. Now that I think about it, there is one situation where this would be really handy though, and that is if you're doing a lot of like surfacing or body panels or something like that, where you have, for instance, we did a roto-molded, injector molded container, right, where we had multiple pieces that bolted together eventually that had very nice curves and like smooth organic geometry between them. And instead of doing that for example, if you were to try and do that with a skeleton sketch where you're only distributing the edge curves, it would be very hard to get continuity between surfaces, between those parts, right? It's much easier to do the surfacing model as one model and then go in and section out the parts. And in that case, we used a there's a feature in here. Can't remember what the feature is called now. It's like save bodies, maybe? Maybe save bodies. Save bodies, maybe.
Yeah, it was save bodies. So what we did was we'd slice out the organic model into its different components and then save those bodies out, and those bodies were imported into parts, and then you made your final edits and stuff like that, having those surfaces already there. So I could see that this might be a superior workflow in that situation, or maybe it's a combination of the two, where you're creating a skeleton sketch folder file or folder part that has, your core just sketch geometry in it, and then you're creating another part file that's going to be like your master model, and that only has your organic stuff that's tricky to do like curvature continuous without having the other surface there. So maybe you're doing like a combination of the two. You have skeleton sketch, you have this master model which has a lot of your organic in it, and then you have your derived, and you're inserting your organic features into your other parts to kind of like do your detailing work. So that might be an interesting use case for it. No, you do share the skeleton. Well, you can share the skeleton sketch part file, but since it's one file, you're only one person can have it checked out at a time. Like, I'm thinking like, if you have a team of engineers, right, and you're trying to distribute information between them, but you have to keep that revision control.
only one person is going to be modifying that file anyways. And you have to be careful because as they modify it, that's going to push updates to all those other parts that are being built off of that. So you can share that skeleton sketch like part. You can all work off of it at the same time because it's just bringing it in as a reference and then you're deriving the sketches from it. So you're not actually editing or doing any work within that part file. So more than one person can have access to it and can edit from and can design from it, but they can't edit it. Abood, there's nothing in the chat. There's no file to open in the chat. If you want to send in a file, you can send it to info@forgepd.com. Yeah, depending on how many people are working on the project. Yes, exactly. And that's the same with the skeleton sketch, right? Like if it's just me working on it, I might put more or less detail in there depending on, you know, how I'm going to build the parts on the back end. So, and that makes sense. Yeah, and I think that's all as far as like sharing surfaces. I think that makes sense. And the same with the skeleton sketch method. You can't edit that folder part unless you have access to it. I think the only slight advantage would be that unless you're sharing surface models using the master model technique, if you're not doing that, part of me says go skeleton sketch, because then the likelihood of you needing to get in there to change geometry is lower. You'd kind of just be changing. You'd only be trying to access the skeleton sketch if you're trying to change something that is a relationship to another part. So I think that having that hard cap on, if this is relationship geometry within a sketch and it can get shared, it goes in the skeleton sketch. Whereas with the master model, it's kind of a tricky slope of how much do you model in the master model. And if you're trying to take out all the modeling, then basically you're just putting sketches in anyways, and then it becomes which is more efficient from the SolidWorks back end of, is it smoother to import in a part and have all the sketches be there, or is it smoother to derive the sketches in and do it that way? How do you control other people's access with a skeleton? So you would, how do you control other people's access with the skeleton? If you'd only have, are you using a vault or not? If you're using a vault, it's pretty easy because only one person can have it checked out at a time. Boodaboo, let me know if you send that part file or send that file, and I'll refresh my email and look for it. If you're using a skeleton method, can you send an assembly without the part file to all the skeleton sketches? I include the master part in this assembly because we're turning it prof. Yeah, yes, you can. You can, like the assembly that we did for that linkage,
instead of dragging the parts in and making duplicates in that assembly file, excuse me, instead of dragging the parts in and making duplicates in there, you can just, because they're separate part files, right? So you just, like, they're independent part files, so you can do whatever you want with them. Yeah, I get what you're saying. Like, the only reason you have that master model file in this assembly is so that it's visible to the prod. Oh, okay. So converting entities, like, that's a good example, or that's a good topic that kind of carries over on this, I guess. So we can tear into one of these parts, maybe. Yeah, you know what would be a really interesting test of this is, so we can do an evaluate. Sorry, I'll come back to that convert entities, but I'm trying to think of, like, what would drive you to do one over the other. I think organics master modeling has an advantage, or like surfacing master modeling has an advantage. But I'm wondering how much of a performance hit you take doing this master model versus modeling everything in here. So we can do this performance eval and it'll show you the rebuild time of everything, right? And so part of, maybe that's what I'll do. That might be a good example. So I can rebuild one of these parts using master model, and yeah, I can rebuild one of these parts doing master model, or not master model, doing skeleton sketch, and then we can compare, like, rebuild times, and then you kind of apply that to larger assemblies, and those rebuild times start to add up. So that might be something to do. Yeah. So your sketches are in here, right? Okay. Whoa. So it just collapses everything down and then just brings in the body. That's interesting. All right, so convert entities. All right, so convert entities is a feature within a sketch. So if we just go into a sketch, it's a function, it's not a feature technically, because it doesn't add to the feature tree. But it is, where is it? Convert entities right here. So there's a couple different ways to bring, basically everything under convert entities is a way of bringing in geometry external to that sketch and using it as reference. So the most basic function is usually convert entities, and it'll bring up this selection box. And what you can do is then you can select entities, whether it be usually it's edges, is what you end up doing, but I believe you can also sometimes, yeah. So surface is not so much, but usually it's edges that you end up bringing in. And what it does is, say we grab that here and this here, right? When we click the green check mark, I'm just right clicking to select all. You can see that we're sketching on the front plane, and basically what it's done, it has converted the entities that we selected into sketch geometry and on the plane that we're sketching on. So now we can do things like, say we want to, and if sketch geometry has been converted, because it'll have this little thingy here that basically says on edge or some form of this. Or if you select on the entity itself, it'll say on edge. And basically what that's saying is, Solidworks is saying that this geometry is being controlled exterior or in reference from this sketch. So we can convert things in order to design around them. Like say we converted this in and we want to make, change all of this to construction. And then we want to, I don't know, maybe we want to make like a pin that goes through here or something. So we want to make a pin that, is offset from here by 10 thousandths. Right. And so now we have the thing that we're concerned about, which is this offset being maintained. We don't really care what the diameter of the pin is necessarily. We just want it to fit within this hole. And so you can convert all kinds of, you can convert straight edges to and do a whole bunch of different things. But that is the basis of convert entities, is to bring in exterior geometry to a sketch so that you can reference it and create relationships to it. And now the nice thing about this is that this does update, right? So say we do an extrusion here. Let's just do through all both ways, right? So say we extrude this body and now we have a pin here. But say maybe before we do that, we go back up here and we make some change, right? So one way we could make the change is by moving face, and we looked at this in a previous session, right? So we're just offsetting by, I don't know, maybe 10 thousandths, 15 thousandths maybe. Right? And so we can see that we're going to end up making this hole smaller. And so now we make this hole smaller and our pin is now smaller. See how we've we've obviously made this difference. We can suppress this and now everything grows, right? And that's the power of convert entities, is you can take geometry from outside of the sketch, reference it, and then as it changes, everything will parametrically update, which is like the main reason to be using Solidworks, is to create these parametric relationships, whether it's skeleton sketch or master modeling or equations or sketch relations or dimensions. All of this stuff, all the stuff that we talk about on a daily basis and use every day, is to create models that update automatically. That's what we're trying to do. We're trying to say, this is our constraints, this is what we want. The matrix that we build in between is basically saying, if I change a constraint, I want a different outcome in geometry. That's what we're ideally trying to build. And then it's just a matter of figuring out the best way to build those relationships within the system. Okay, so is it safe to use? Absolutely. I use it all the time. The best thing to do technique-wise is to be careful of what you're converting. So, for example, let's see here. How can I break this? So we have this geometry here, which is updating and doing what we want, right? And that's all well and good, but say somebody goes back in and for whatever reason we want to keep that pin, right? That's a good example. Say we design this pin in here, right? And then we use the save bodies and we save out this pin, and now it's its own part that exists somewhere, right? But it's still being generated from this feature tree. Now say somebody goes in and they're like, oh, hey, we're no longer doing this 4 lug thing, we're actually just going to do a 3 lug thing, right? And so you're going to delete this entire lug, right? Poof, lug is gone. Now watch what happens. Things break, right? Even if you suppress this, right, this is still broken. And the reason it's broken is because the geometry it was attached to no longer exists. Right, which is bad. Now, that lug still exists in different places. So, like, one thing we could do is be like, all right, well, we just got to change where this is assigned to, right? So we go over here and we would convert our entities and we would fix the problem, right? But the best way to do it now I have to find the sketch, but the best way to do it would be to reference the sketch geometry, which is in one of these somewhere. Bearings, screw, here we go, screw tab, right? So the best thing to do whenever you're doing anything in SolidWorks, you want to use the most stable geometry you can. And like I've been saying this session, that's either going to be these planes here in the origin, or it's going to be sketch geometry, usually. Because you very rarely, like in this instance, we only drew it once and then we patterned it, right? So you're not going to delete this hole unless you're removing it from the model, in which case you probably don't need that pin anymore. But for an example, so we can show this sketch, right? And it looks like we can't edit it, which is fine. But if we show that sketch, right, we can go in here and we can convert this sketch, right? So now we have that conversion, but we're converted to the sketch, not this edge of the hole. So if we, we'll just do this. So if we make that co-radial, right? So we have converted the sketch entity, not the whole entity. So now when we go and generate this pin, it works, right? Our pin works. And we have the same offset control that we did before. So say this face goes in and gets moved. Now it won't work this way because we're moving the face instead. So that's something that we'll have to work on. But if you're going to move this face, you'd likely go in and change the sketch, not the, not go in and just make some, like a single face offset move. But the nice part is that even if we delete this face, our pin still works, right? And that's just, I mean, it's kind of a ham-fisted example, but it's basically to show that it's what you're converting that matters, not necessarily the convert entities tool that's good or bad. Avoid using convert entities from geometry, correct. And try as much as we can to convert on the sketch, correct. That's basic. That's the basics of it. You want to convert whatever the most stable geometry is. Like for example, if you're creating geometry in this sketch again, and we want a line that goes through the origin, right? That's, I don't know. Oh yeah, this is a good example. Say we want this point to be on the origin, right? Or this axis, and we know that's the origin. We want to use the origin as the point, right? If you want an angle here, right? You could convert this in and then do some type of angle, right? We can convert this in and do some type of angle here. But you'd be much better maybe doing an angle off of that plane, right? Because we know that's not going to move or something. And obviously it's all dependent on what you're trying to build and what relationship you're trying to make. And that's all dependent on the project that you have. All right, guys, I think that's going to wrap up today. I know we didn't get into equations very much. Who was it that wanted to do equations? Yeah. I think Stephanos. Yeah. I see Corals. I see Coral is confused on whether or not it was indeed him. I am done today, but I am around tomorrow for sure. So if you want to send me like a meeting invite on that, that'd be fine. Yeah, Stefanos, I'll try and come up with an equation thing. I think the gear would be a little too. I don't know. I'll look and see if anybody who does a gear out there does a parametric one. Because if that's the case, if nobody has like a good video on how to do a parametric gear, then maybe that's what we'll do. Instead of like just doing how to make a gear, we'll try and tear into some equation stuff and like how to build a parametric gear. And then we can probably do that herringbone or do like a herringbone design of it. That might work. All right, sounds good, guys. I hope this was helpful to you guys. If you have questions or models you guys want me to look at, definitely send them to the email. I tried to be less rambly today, or at least a little bit more on point, but sometimes just talking through stuff is like I'm just filling air with thoughts. So hopefully it was useful. All right, you guys have a good night, and I don't know when the next live stream will be. Now that this Hinge is finished up, I got to circle back to some other client projects which I can't put on air. So I will try to do a video, or we'll do a live session on the equations, and then we'll kind of go from there. Maybe tomorrow afternoon. It seems like the afternoon sessions are better attended. Abu, there's no link that's coming through, buddy. So I don't know if YouTube is scrubbing them out. It could be. Oh yeah. Okay, now I see it's going through, and this looks like it's redacting links. All right, guys. I will talk to you guys tomorrow. Yeah, we'll shoot for tomorrow afternoon. I think this worked pretty well, so we'll go from there. You guys have a good night, and we'll talk. See you guys in the next one. Best place to send models is info@forgepd.com. So that's the email. Appreciate it, guys. You guys have a good night.